The broadcast is now starting. All attendees are in listen-only mode.
Hi everyone, this is Dave from Developintelligence. Thanks for joining us today for our webinar on the new features of Java 5, 6, and 7. The presenter today is Kelby Zorgdrager. He's the president of Developintelligence, and I'm going to turn it over to Kelby.
Hi everyone, thanks for joining us today on the webinar. Let me just start off with a quick little background on Developintelligence. Developintelligence is a technical training company. We specialize in providing highly customized role-based learning solutions to software teams. Last year as a company we delivered training to close to 1,800 engineers globally. Since we started, we've delivered training to about 40,000 engineers worldwide. We do specialize in the areas of Java open source web development technologies and mobile apps, and we are headquartered in Boulder, Colorado. Myself, I started working with Java in 1996. JDK 1.0, actually started working with it as an alpha. Throughout my career, I've had many different positions. I was a Java platform engineer at Sun for a couple of years, and have also taught a number of engineers globally Java and related technologies. We have about an hour to talk through some of the new features in Java, and we're going to spend that time first with a quick overview of current state of Java and where it is in terms of different versions, and then we're going to look at some new language features that have come out over the past 3 or 4 years. As I mentioned, we trained about 1,800 engineers last year, and I would say approximately 50% of those engineers are still using some version of Java 4 or some version of Java 5. Even though Java 7 has been out for a while, there's still a fair number of people that are using previous versions. So we thought we would just spend time going through those different versions, what features were introduced during those different versions, and help you identify some new language features that you can adopt within your own programming. So Java 5, if you're not much of a historian, was released in 2004. As I mentioned, about 50% of the engineers we delivered training to last year are still using Java 5. You'll notice that Java 5 was end-of-lifed by Sun back in 2009. Basically what that means to an engineer and to a company that is using Java 5 is that at some point in time in the near future, potentially in 2014, Oracle will quit providing public builds of the platform and of the JDK, which means as a company you would have to go into a support contract and buy a historical version from them. The most current version, which you can still download from Oracle's JDK archive site, is 1.5 update 22. There are ports for all modern operating systems. 2006, Oracle or Sun released Java SE6. There weren't any really new language features introduced during that time. Java SE6 was really focused on making some of the APIs easier to use, increasing the efficiency and the performance of things like the JVM and the compiler. And then if you were to look back, Sun started to introduce scripting support into the virtual machine, allowing people to use dynamic languages, whether it's JavaScript or Groovy. The current version of JDK 6 or Java 6 is 1.6 update 43. Again, you can grab that from Oracle's download site. The most current release of Java is Java 7. It's been out for about 2 years, released in 2011. Just like in Java 5, Java 7 did include some new language features. All along the way, every release of Java from day one through today has included new APIs, new classes, new functions for engineers to create more robust solutions. There have only been a couple of times since the language was originally released where Sun introduced new language features. Again, that's in Java 5 and Java 7. Java 8, which is slated to be released in 2014, will also have some new language features. The most highly controversial of the language features that people talk about right now is the idea of closures, also known as lambdas. just to give you kind of an idea of how Java has grown back from its early days, most people would say that the first true production-worthy version of Java was JDK 1.0.2, so that's where our graph starts, and it brings us through today. What you'll notice is that over the past few years, Java has grown from a small handful of classes, 200 and some odd classes, all the way up to a very, very large set of libraries. Current state of 1.7 is that there are about 4,000 classes that are available to us as engineers. What that really means from a development perspective is that it's no longer easy to spend a weekend reading a Java in 21 days book or a Java in 24 hours book and learn the language and learn the capabilities. It's a much more lengthy process. It takes more of an investment in terms of time. You will also notice that the package growth has grown a little bit. If you were to actually kind of just graph the growth, the percentage change in Java, you'll notice that over the past couple years, less and less investment has been made in terms of the libraries and the packages compared to the early part of the Java language. My personal feeling is that part of the growth, part of the reason that the sloth has grown down is because open source products, open source foundations such as the Apache products and the Spring projects and some of Red Hat's projects have taken some of the burden off of Oracle and allowed the community to really drive where Java is going and what engineers find useful in creating enterprise applications. So let's just kind of move into some of the language features now that we've seen how Java has grown over the past number of years. The way that we're going to go through the language features is pretty code oriented. You know, most of the classes that we teach, we like to have a 40%, 20%, 40% split, where we're spending 40% of the time lecturing, 20% of the time doing architectural conversations, and then 40% of the time doing hands-on coding. In a webinar format, obviously, everybody doing hands-on coding would be a little bit inefficient. So we have some prepared code examples that we will just look through together. The first language feature that we've got here is something called static imports. And for those of you who have been doing Java development for a long period of time, you'll probably remember a pattern from Josh Bloch's book, Effective Java, on how to create an interface that contains a number of static final variables. And as a developer, I could go ahead and implement or access that interface to have kind of quote-unquote constants, global constants within my program. What we would find if we jump back 5 years is a lot of code that kind of breaks good object-oriented design, where classes implement what I would call kind of tagging interfaces. With the introduction of static imports, that's no longer required. What you can see here is that with the static import syntax looks very similar to the kind of traditional Java import syntax. The only new word there is the keyword static on lines 3 and 4. And what that does is that gives us direct access to static variables and static methods. So for example, on line 15, I have access to the static variable pi in the math class without referencing it using the class name. And on line 16, I have direct access to the static method round, again found in the math class. Just like in standard import semantics, static imports do include what's known as an on-demand qualifier. That's that splat everybody's probably familiar with. Whether this is a good or a bad idea kind of really depends on your perspective of how to optimize code and how to be explicit within your code. But for simplicity's sake here, you'll notice that we've collapsed those two static imports into one static import. Use that on-demand syntax with that star there. And then you'll notice on line 14, I can go ahead and directly access again math.py, dropping math as a qualifier, and I can go ahead and directly access math.round on line 15, again, dropping that qualifier. Static imports, you know, they are useful. To be honest, in my experience teaching developers, there's not a lot of developers that use these, though they are available to us. In 1.7, prior to 1.7, creating binary literals within the language was nearly impossible, if not a challenge. So 1.7 introduced into the language is a native notation for us to denote a binary literal. Starts off with 0B, and then obviously binaries, ones and zeros. So you can go ahead and specify your number. Sometimes when I'm working in financial institutions, or I'm working in insurance institutions where I have large account numbers, or I have large identifiers that are constants, the numbers that we create as developers are a very long sequence of integers, or a very long sequence of integer characters, and are sometimes hard to read. So in 1.7, there was the introduction, or there is the introduction of an underscore that basically just functions as a comma, so to speak, purely just there for legibility of code. The compiler gets rid of it upon compilation, doesn't show up in the bytecode. So again, it's purely just there as a nicety for code reading. In 1.7, one of the biggest complaints of the Java language that I have heard from about 1998 through 2011 was how strings were treated by the language. In most of the competing quote-unquote web-oriented languages, whether it's JavaScript or PHP or Ruby or things like that, strings are treated as first-class citizens. In Java, they have this kind of hybrid approach where they're partially primitives, partially references. At the end of the day, they're really references. And the party line that Sun carried for a long time was that because strings are references, there's no way that you could use them in a switch statement. Well, it turns out in PHP and some of the other languages, strings are implemented as references as well, and they work in switches. So in 1.7, Oracle finally caved and said, yes, you're right, developer community, we should be able to switch on a string. So here's a real basic example. Remember that strings are case sensitive, so the string hello with an uppercase H is different than a string hello that's all uppercase letters. So in this little example, we go ahead and switch on the value of the string hello. We've got 3 different cases there: lowercase, mixed case, and uppercase, and then traditional switch case break semantics apply. So that's definitely a nicety when we're working with kind of a web front end, building a web front end, and request parameter data is sent in as a string. I need to determine what the value of the string is, and I don't want to have if else type of blocks. 1.5, there was a feature that's added called autoboxing. You may or may not be familiar with this. Autoboxing really should be called autoboxing and auto unboxing. It's the automatic ability for an integer reference to be converted into an int type, and vice versa. Prior to 1.5, especially if I'm doing web development programming, where I'm receiving strings and I need to convert a string into an int, and then I need to convert an int into an integer to place it in a collection or a user session, I wrote a bunch of boilerplate code to do the conversions. 1.5 gets rid of that. You'll notice on line 13, I take the primitive value 32, I store it into the integer reference x, and now x is a well-formed integer. That's an example of auto-boxing. On line 17, you'll see an example of auto-unboxing, where I take the integer reference, convert it down to the primitive type, and then I multiply it by 2, storing the results 64 into the primitive variable y. Auto-boxing and auto-unboxing obviously comes into play when I'm dealing with collections. Here's a real simple example where I've got a hash map. A hash map is just a collection of key-value pairs. Generally, my key and generally my value are both objects. Again, prior to 1.5, if I wanted to store numerical values as a value in the key-value pair of a hash map, I would have to convert that literal value into a reference and then place the reference into that hash map. So as an example here, I go ahead and you can look on line 21. I've got something called word count. It is on line 17. It is a primitive integer. And you'll see on line 21, I go ahead and place that primitive integer into a hash map. Again, hash maps only contain objects. So behind the scenes there on line 21, that word count is going to be auto-boxed into an integer object, and the integer object is going to be placed into the collection. The same thing is true if I were to retrieve a value from that hash map. For example, on line 27, remember behind the scenes that hash map now contains an integer object that represents word count. So on line 27, when I call wordmap.get, passing the value for the key, you'll see that it's going to return back to me an integer object. Using that casting semantic along with the auto unboxing behavior that's available to me, the value is stored now into that primitive integer value. So a couple of very basic examples there of showing you how auto boxing and auto unboxing make your life as a developer a little bit simpler, again removing some of that boilerplate code that we saw prior to 1.5. Autoboxing is supported across all the primitive types, as you would expect, and again it works both ways, from a primitive to a reference and from a reference to a primitive. There are still in 1.5, 1.6, 1.7, 1.8, there are still those convenience methods that allow me to convert a string into a primitive value, so a string representation of an int into an integer value. There is no auto boxing mechanism to do that for us. We still manually have to convert a string into an int. And that's part of the side effect of working with a strongly typed language versus a weakly typed language. Another nice feature in 1.5 that was introduced is the idea of a for each loop. I'm sure everybody's familiar with the traditional C syntax of a for loop. The C syntax has kind of that initial condition, the test condition, and then the limit. All three of those conditions are separated by some semicolons. In 1.5, the notation of that for loop has been simplified, where I have like, for example, on line 15, a variable called S. I've got my collection of data called args. S is the placeholder for each one of the elements that is popped off of that collection. In this case, what's going to happen is that as we traverse through the for loop, or as we traverse through the array, the for each loop is going to function just like a regular for loop, starting it off with index 0 and going to the end of the collection. One of the disadvantages of a for each loop is that you do lose the ability to identify where you are in terms of the index counter of that collection. So I would say my terminology is that for each loops are generally used to retrieve and not necessarily modify or reposition elements in a collection. For each loops do work with arrays. They also work with iterable types. So here's another example where I've got a list. On line 15, I convert the argument array into a list. And then on line 18, I go ahead and iterate over the list. And what's going to happen behind the scenes there is that arg list, the iterator for that arg list is going to be retrieved automatically. The iterator then is going to be used as I traverse over the list. And the logic behind the scenes is that, again, the runtime environment is just going to pop each element off of that iterator, store it into that argument. In this particular case, I print it off. So pretty straightforward syntax. If you've ever done any shell scripting, it should be very familiar to you. Another nicety in kind of standard Java 5 language features is the idea of a variable argument list. Prior to 1.5, if you wanted to create a method that took a variable number of arguments, meaning 0 through infinity, you as a developer would have to create a method and include in the method signature a variable that represented an array. And then as a developer, you could see on like line 20, I would create an array with the values that I want to pass in, and then I could go ahead and do the processing of that variable argument, for example, like on line 27. While it wasn't very hard to create a variable argument within traditional Java language syntax, it was, again, a little bit cumbersome. I, as a developer, would have to create the array with the contents for the variable arguments, and then I would have to pass the array. In 1.5, that syntax became a lot easier. What happens, if you notice on line 21, is that the signature of the method changes. The way that I describe a variable argument no longer is with the array notation. Instead, it is with the ellipse notation, so 3 dots. And you'll notice on line 18, now when I go to pass in the variable number of arguments, I just call the method. I specify the variables using commas. Behind the scenes, what's going to happen is that the virtual machine is going to take book 1, book 2, place those 2 variables into an array, and then pass the array down into titles. So that's why when you look at line 23 through 27, when you look at the processing code, you'll notice that titles is actually an array. It functions like a regular array. It has a type like a regular array. It has a length like a regular array, and I can traverse through it like a regular array. So the result is that, again, the compiler is doing some nice little magic for us to make our life easier. Not rocket science, but makes coding variable argument array methods easier. One of the biggest features added to the Java language in 1.5 was the idea of enumerations. So enumerations historically represented or do represent a closed mathematical set, a constant of values, so to speak. One way that people created an enumeration was, again, they would create an interface, and in that interface they would create public static final variables, and the values of those variables would never change. While that was an easy way to work around, to circumvent the fact that the language does not have or did not have enumerations, again, it wasn't a very good object-oriented semantic. So starting in 1.5, Sun introduced the idea of enumerations. Enumerations are treated as well-formed types, meaning they are a first-class citizen within the Java language. Enumerations behind the scenes, if I were to dissect them like I were to dissect a frog, I would see that enumerations are implemented using static final variables like I saw in an interface. But they are stored with a little bit more logic than in a straight-up interface. What I would also find is not only are they stored as static final variables, there is a name associated with each enum instance and an ordinal value. I could use an ordinal value to find an enum instance in the set, but generally that's not good coding practice because the arrangement of the set could change. The other thing that is introduced with enumerations, and the other reason they were created as a first-class citizen or a well-formed type, is the fact that types in Java, first-class citizen types in Java, have the ability to store not only data but also behaviors. So if I were to compare the new enumeration syntax against the old enumeration syntax using interfaces, the old enumeration syntax with interfaces did not provide the ability to define methods that worked on the enumeration values. The new way with the first-class citizen, the enum type, I have the ability to create methods that allow me to work on the values. So here are a couple of examples. Neither one of these examples show you how an enumeration can take data and apply to it behaviors. Both of these examples just show you static data within a set. The first example is kind of a top-level representation of an enumeration called days, represents the days of the week. Standard coding convention is that all constants in Java usually are written as uppercase characters. So there are my days of the week represented as the uppercase characters. If I were to look at the ordinal value for those different values in the enum called days, the first element of that set, which is Sunday, would have the ordinal value of 0. Again, usually we don't want to use the ordinal value because somebody could go in, change the order of the days of the week, and make Monday the first day of the week, or make Saturday the first day of the week. So coding against the ordinal value isn't necessarily a great strategy, though it does work. Second example there just shows you how I can create an inner class, so to speak. I can create an enumeration that only exists and only makes sense in the context of a calendar. So in order for me to identify the days of the week, I would use something like calendar.days.sunday to reference Sunday. Again, days of the week there does have the ordinal values, the arrangement's the same, so on and so forth. So pretty straightforward to create an enumeration. Accessing values within an enumeration, I'm just going to use standard Java syntax, standard Java dot notation. I'm going to use the enum type, its class name, as a qualifier. I'm going to use a dot, and then I'm going to follow that by the enum instance. And that will give me access to the value. Each enum value has, as I mentioned, both the numeric representation and a string representation. I can use the toString method if I wanted to retrieve the string representation of an enum value. I could use the ordinal method to retrieve the ordinal value, the numeric value, if I wanted to. But there are also some other methods, some convenience methods that I could use in working with enumerations. Generally, when I'm working with an enumeration, especially if I'm doing some form of data processing, I will receive my data input as a string. I want to convert that data input into the actual enum instance type to make sure it is a valid, quote-unquote, valid enum type. So there is a method called value of that allows me to take in a string, and it's going to convert that string into the physical enum instance. Value of is going to be case sensitive because strings in Java are case sensitive. So if I'm going to use the value of method effectively to convert a string into an enum instance, generally the best practice would be for me to uppercase the string before I pass it to the value of method so that the matching works out properly. You'll also see a little bit lower down on the slide that enums, again, since they are kind of well-formed types, and each instance of an enum is an actual Java object, you'll see that there are the standard methods that I could use, toString equals hashcode. In fact, because they are standard Java objects, I could also use an enum instance in my threading if I wanted to. I could, for example, grab the lock of the Sunday instance from the previous example and synchronize on that. So well-formed objects. So here's a real simple example of accessing an enum value. Again, assuming my enum is called days, I have an enum instance called Sunday. On line 10, you can just go ahead and see that I would say days.sunday to grab that instance. On line 11, some very basic Java code taken out of the Java for Dummies type of book, where I'm just taking a variable today, allowing the println method to do its magic to convert today into a string, a FIDE representation by calling toString, and then I print out the value. If I were to actually print out the values, the value of Sunday, you would see as a stringified representation that it is Sunday, all uppercase characters. Enums do work with switches. So now I have the ability to switch on an enum type and switch on a string constant. My life is almost perfect when it comes to Java coding. Here's a real basic example. I've got different messages that are created based on the day of the week. Hopefully on Saturdays everybody plays, and unfortunately Monday through Friday everybody goes to work. But you'll see basic switch example. Again, I'm switching on the enum instance called today. Today, you'll notice, is passed in on line 16 as a variable. Going a little bit deeper into the enum syntax. If you recall, I said about a couple minutes ago that every enum instance is a well-formed object. Enums allow me to place to invoke behavior on some data values. So here's an example on line 13 where I've got that instance D. I'm calling on that instance D a behavior called name. Again, that's that is a predefined method that I automatically get as part of the Enum love, and that's just going to go ahead and print off, in this particular case, using that for each loop every single day in that enumeration. Pretty straightforward syntax that we've just walked through. In terms of language features and functionalities, enums are very powerful. Obviously, we can't go through all of the different features and functionalities that are available to us, like constructors and overridden methods and overloaded methods based on instances and things like that, but they do exist. So kind of related to enums in terms of the scale of impact within the language was the introduction of generics. Generics in 1.5 give us a lot of power in terms of how we define not only classes and things like value objects, how we filter out data that's coming into a method, or how we filter out data that's coming out of a method. But generics, in most developers' daily life, generics are typically discussed and typically encountered specifically in the area of collections. So we're going to talk about generics in the context of collections. Again, very large addition to the Java language, very, very powerful addition to the Java language. We're just going to quick look at a slice. The idea is that prior to 1.5, I could create a list of anything. And in that list of anything, I could have a mixed collection of integers, strings, my own types, floats, calendars, things like that, which was fantastic, very powerful. The disadvantage, however, is that when I go to do list processing or collection processing, my code has to take into account all those different variations, all those different types that I might encounter. And if I don't take into account all those different variations that I might encounter, I'm sure you have seen at some point in time in your Java development career class cast exceptions. I'm popping something out of a list. I think it's a string. In actuality, it's a customer. Customers aren't strings. Virtual machine throws up its hands in the air and says, hey, I don't know how to deal with this type conversion. And you would see a class cast exception, one of those runtime exceptions. So type-safe collections, the idea here is to move away from that, raw list or that raw collection that can contain many different types and create some predictability in terms of the data collection that I'm working with. Predictability in terms of adding things to the collection, but also predictability in terms of retrieving things from the collections. Collections have been around since 1.1. That's when the Collections API came out. And it's grown in terms of the capabilities. Some of the other new features that were added in 1.5, 1.6, and 1.7 were the types of collections that I could use and the types of threaded collections that I could use. We're not going to get into that right now, but again, just realize that they exist. For our simple example, we're going to look at kind of the classic example of working with a raw type. Line 14, I declare a list called myList. I'm going to say, hey, it's an array list. It's going to be bounded by some default size. And then what I'm going to go ahead and do on line 16 is I'm going to add to that array list my inbound command line arguments, that args array. And then you'll see on line 18, I'm going to go ahead and add that argument array, a list basically, to my list. So now I've got a list that contains a list, which is great. I can do that. But then you'll notice on line 20, I also add an integer to that list. So now if I were to tear apart my list and I were to look inside of it using my X-ray vision, I would find that my list contains both a list and a single integer, which means when I go through and start processing the list, like on line 25, I could have class cast exceptions, or I could encounter data types I'm not expecting. So while this works and while this is powerful, it also assumes that as an engineer, I really know what's going on in terms of that composition, that internal composition of the collection. And remember, one of the principles in object-oriented programming, right, is to have that decoupling or that abstraction so that I don't need to know the details. If I were to move to the 1.5 way, you'll notice what happens is that not only do I type safe the reference, but I also type safe the physical implementation. On line 14, I type safe the reference by using that diamond operator. Within that diamond operator, I qualify the type that the reference is going to contain, or the type that the collection is going to contain. And then on line 14, when I physically go to create an instance of that list, or the instance of that collection, I also type the instance. So now I've got a reference called my list that can only contain strings. Then I've got an instance of an array list that it can only contain strings. What that means to me from a processing perspective is that when I do the conversion on line 17, that all works wonderfully because args is a collection of strings, so that's great. A string is a string is a string. But if I were to look at something like line 21, it's commented out obviously because it doesn't work. I can no longer add to this Typesafe list random objects. I can't add, like I could in the previous example, an integer. The great thing about that is that when I go to do my processing, again, down on line 25, when I look at that while loop, when I go to do the processing, first and foremost, I don't have to worry about class cast exceptions because my reference and my collection are type safe. And second, you'll notice I no longer have to do the casting because the collection actually contains a variable of that type. The virtual machine, when it does its return or when it does its next, is going to return back a fully qualified or fully cast reference type. So with my type safe collections, I have the ability to have some predictability in terms of inserting, and we saw that on both line 17 and 21, and we have some predictability in terms of retrieval from that collection. Of course, there are ways to sidestep kind of that type safety. If you forget to put the qualifier on my list on the reference declaration, for example, what you could have is that you could have an instance of an array list that's strongly typed, but the reference to that strongly typed array list could be considered a raw type. So there are scenarios, if you do some Google searching and you look at a tutorial on type safe collections, 7 out of 10 times you'll find examples that aren't truly type safe because they drop one of the qualifiers, either on reference declaration or on method variable declaration. In 1.7, while the syntax in 1.5 is relatively straightforward, it feels a little bit redundant. So in 1.7, sticking with the 1.7 theme of simplifying the syntactical representation of things in the Java language, you'll notice that the diamond operator syntax has been simplified. The first example shows you what you would do in 1.5 to create an array list of strings. The second example, which is the third bullet, shows you how to create a type-safe collection of strings, again, in that list representation. What's going to happen is that the compiler is going to say, oh, you know, I'm smart enough to infer the type and do that quote-unquote heavy lifting for you. So that's the you may have heard or you may have read, but that's an example of how the diamond operator in 1.7 has been simplified. Another big introduction to the Java language in 1.5 is the idea of annotations. So enumerations introduced a brand new type, huge impact to the language in terms of functionality. Generics, again, big change to the language, a lot of robust things that I can do with generics. And then the third major change to the language is the annotation mechanism. Annotations have been around in the Java language for a long time. They were just never interpreted by the compiler, and they were never interpreted by the runtime. The annotations that I'm talking about are the annotations that existed in JavaDoc. JavaDoc is a command line tool. I'm sure you're familiar with it. And it does text processing. When it does text processing, it looks for a very specific syntax, that @ symbol, and it treats that @ symbol with a special behavior. Annotations in the Java language have the same type of idea, or it is the same type of idea. The compiler now, when it's doing text processing of my source code, it's going to look for annotations that are placed outside of JavaDoc comment styles, applied directly to class signatures or method signatures or field signatures, and then perform some special behavior. The annotations go one step further as well, and the virtual machine, the runtime environment, has been changed to support runtime discovery and runtime quote-unquote application of annotations. Annotations in the runtime world are commonly used in things like CDI. They're used in just straight up Java EE dependency injection. They're used in frameworks like Spring and Seam and Struts2 and things like that. So one way to talk about annotations is the idea of this metadata facility. Another way is that it allows me to create my own tooling support for the Java language, where I can do auto generation of source code, or I can do dynamic bytecode creation at runtime to deal with certain scenarios. Very basic example just to show you how annotations work. Again, you'll notice I'm going to use the @ symbol, borrowing that syntax directly out of JavaDoc. In this particular case, I'm applying that annotation called override to a method toString. In this particular example, if you were to look very closely at the method toString, we should all know that toString is an inherited method from java.lang.object. We should also all know that toString has an uppercase S in it. If I were to look closely on line 11, you would notice that toString does not have an uppercase S. It's got a lowercase s. When the method signatures are slightly different in terms of method names and the casing of method names, historically the compiler would say, hey, you know what? You are adopting a method overloading syntax. So what would have happened historically is that override example would contain two methods that represent toString. It would contain the inherited toString with the uppercase S, but it would also contain the lowercase toString with the lowercase s. Two different methods, two different behaviors because of method overloading. Great way to have bugs in your code and never know what's going on. So with the introduction of this override annotation, what's going to happen here is that the compiler, when it compiles this code, it's going to look in the inheritance hierarchy. It's going to go traverse up that inheritance hierarchy and look for a method somewhere in this child's parent structure that is called toString with a lowercase s and returns a string. If it doesn't find a representation of that method in the inheritance chain, then what's going to happen is that the compiler is going to complain and say, hey, you know what? You declared a method to override a method, or you declared toString to override an inherited method. It doesn't do that. So here's an example at the bottom there showing you how the compiler will warn you and actually fail on compilation if I use the @override annotation on a method that should be overridden and the method's signatures are out of sync. There are other annotations that are constantly added to the language in 1.5, 1.6, 1.7, and in 1.8. More annotations will be added, but 1.5 was the first place that they showed up. Because annotations like enums are first-class citizens, I can create my own annotations. The syntax to create your own annotation looks very much like the creation of an interface, except again, I'm going to use the @ symbol. Covariant returns. Covariant returns, the idea behind this is that based on the strong typing of the Java language, if I had a child method, an inherited method, a child overriding an inherited method, there are certain circumstances where I want that child method to narrow the return type. The covariant returns give me the ability to do that. And have all of the method mechanisms and all of the casting mechanisms work properly. Real basic example, line 15. I've got a method called getName. It's in a class called parent. We've got another example called child. Line 13. It also has that method called getName, and you'll notice I'm using that @override annotation, but I have changed the return type to be a string. So I have narrowed, in my terminology, I have narrowed the return type to be a string so that when the caller interacts with the child's getName method, they physically don't have to take the object return type, convert it into a string. In this particular case, it removes that casting. Covariant returns were partially introduced to support or aid support for generics, but they also give us the ability to have tighter code. One of the major features in Java 7 that was added is this idea of an auto-closable resource. I'm sure as Java developers, if you've been writing Java code for a while, you are familiar with the boilerplate try, catch, finally code from hell, where you have a number of catch blocks to deal with a try. or you have boilerplate code where you open up a resource, you use the resource in the try, and your catch only does one thing, and that closes the resource. The try-catch semantic in 1.7 has been simplified, again, allowing me to focus more on the logic of what I'm trying to write than creating a bunch of catch blocks. So here's a real simple example. I go ahead and create a file input stream. When I go to create a file input stream, you'll notice in the new way box, I declare that type FIS in a parenthesis structure within a try. What that's going to do is that's going to tell the compiler that FIS is an auto-closable resource, which means that if an exception occurs or if the try block executes properly at runtime, the runtime environment will auto-close FIS for me. In this particular case, input stream has been rewritten to be auto-closable. Auto-closable is the interface that tells the virtual machine, hey, go ahead and perform whatever the auto-closable functionality is, which in this case is just going to be closed. So you can see there that simplifies some of the boilerplate code. Another simplification dealing with try and catch is that instead of me creating a very long structure of catch blocks, I can create a try block. I can then have a catch block, and in my catch block, I can use the OR syntax, the pipe syntax, and tell the environment at runtime, hey, if you encounter an instantiation exception, or a no such method exception, or an invocation target exception, go ahead and do this particular thing, which would be log the exception and rethrow it. So you'll notice here, because of the OR syntax, I now have a simplified representation of a catch structure. So that's a quick insight into some of the language changes in Java 5, Java 6, and Java 7. If you notice, there aren't a huge set of language changes in Java 7. There's maybe 3, maybe 5, just a handful of changes. The biggest changes in Java 6 and in Java 7 really are on the APIs. Java 7 introduced something called NIO2, which is a new IO, which has a better representation of an underlying file system, file descriptors, things like that. There are also additions in both 6 and 7 around threading to make threading easier to do. There are some changes in some of the core XML processing APIs, things like that. But because we only have 45, 50 minutes today, obviously we could not go through everything, and hopefully that was a good glimpse at some of the language changes. As far as how we can help you as you're transitioning from Java 4 to Java 7 or Java 6 to Java 7, if you need just a little quick start and helping you understand some of those features and how to better apply those features, or if you're looking to understand some of the new APIs and how to apply those new APIs, generally we can come out and deliver a customized training class for you and your group within 2 weeks. So we have some pretty fast turnaround time. All the customized classes that we offer, we customize the content for free. Usually when we're doing customization, we'll have a conversation with you. We'll talk about what you're trying to achieve with the learning, what your experiences are, and then we'll put together a customized content agenda using your tool set, your operating system, your app server, things like that. And as far as pricing goes, we're not the most expensive training provider out there. We're also not the cheapest training provider out there. It's primarily because everyone who works with Developintelligence has been writing Java code since 1996. Some of us have been writing it since it was kind of an alpha. So you'll get a lot of years of experience behind you and helping you learn Java. With that, I'm going to go ahead and turn it back over to Dave, and Dave, you can field any questions if there are some.
Yeah, thanks, Kelby. We have a few questions. The first is that are people still really on JDK4?
That is a great question. It is I shouldn't say every, but I am constantly amazed at how many companies are still using JDK4. I'm not gonna pick on any sectors, but if you have health insurance or you use a debit card or a credit card, there's a high likelihood that those production systems are probably still running on 1.4.
Okay. Another question: where is Intelligence located?
We are located in Boulder, Colorado, but we have clients all over the world, from China to Belarus to Israel.
Okay. And how is our training delivered?
That's a great question. Every time we deliver a training class, one of the steps that we'll go through with clients is to figure out what is the correct modality, which is a training terminology. But what's a correct delivery format? Usually engineers like live instructor-led training, where our stinky, not very well kept, that's a joke, instructor shows up and teaches on site. Most of the time when we're teaching in a live format, students will follow along with live coding. We'll create examples in the class, and then, like I mentioned, about 40 to 45% of the time, students will actually write code and create projects.
Okay. Another question: when can we expect Java 8 to be released?
Yeah, that's a great question. Originally, it was supposed to be out, or historically, it was supposed to be out by now. I think the debate around closures has delayed Java 8. The latest that I have heard is March of 2014, but I'm not a gambling man, so I'm not going to put my money on that.
Okay. Yeah, and that's all the questions we had to address here. There's a few people I'll reach out to personally.
Great. And in parting, there is contact information for both Dave and I, toll-free number, email addresses. We are going to be raffling off a free Safari account. We do bundle Safari books online with every single one of our courses. So we have a little question. If you want to be entered into the raffle, go ahead and just post an answer to this question either on LinkedIn or Twitter. Everybody who supplies the correct answer will be entered into the raffle. If you win, you will get an account to Safari that's good for a year. It's worth over $300. The question is, what date did the first customer ship of the JDK occur on? So go ahead, figure that out. You can use Google to figure that out. Post your answer on LinkedIn or Twitter, and we'll announce the winner on Monday.
Thanks
For the
everyone
time today, and we hope it was useful.